Alright, so we come to the statistics part of the course. So what we need is we need some introductory definitions and notions. So that's what this lecture is about, right? Alright, okay, so what we're dealing with is we want, well, first of all, we're going to be looking at populations, right? And a population consists of the total set of observations with which we are concerned, right? So, for example, if we're interested in the heights of Trinidadians, this example over here, right? Then the set of heights of all persons in Trinidad, right? That's a population, right? What we may not be able to do is we may not be able to actually ever record all heights of all the persons in Trinidad. So what we do in statistics is we sample somehow to get an idea of usually, well, what the mean height or would be, right, and what the standard deviation would be, right. So let's assume somehow that by a census or so, we have a list of the names of all Trinidadians. Right. Well, let's say consider a simple case. So what we want to do is we want to estimate what the mean height is, right? Of what the average height is of a Trinidadian, right? Okay, so one way to do that is, well, we have this list of names here, right? And what we do is we select one name from the list, right? Okay, so we somehow select that one name. It is, let's say we select that name randomly, right? Okay, so we have that name on the list. We don't know the height of the person as yet, right? We didn't measure it as yet, right? So the height of that person is actually unknown at this point in time, right? And what we do is we say, well, okay, it's an unknown, right? So we're gonna call it X over here and we call it big X, right? Okay, now part of doing the statistics, right, is that variable over there, this big X, we're going to assume that it has a certain type of distribution, right? And that's key for the stats that we're going to do for the rest of the course, right? We assume that the the height is going to follow some type of distribution. Usually, the distribution would be normally distributed, although sometimes we do not need to know what is the form of the distribution, right? Anyway, but to start off with, we have the name of the person. We let big X be the variable that represents the height of the person, which we don't know as yet, right? And we assuming that big X is normally distributed, right? Okay. And the goal over here is to start off with is you want to estimate your parameter mu over here. So you want to get an idea of what the mean height is, right? And eventually what we'll need to do is we want to estimate what your variance is over here, sigma squared, right? Okay. Right. Okay, so up to this point over here, we don't know what the height of the person is, right? It's still an unknown x, right? But what we do know is that that big X over there is normally distributed, right? Okay. All right. So what we do is we now, after some effort, we manage to locate the person and we measure the person's height, right? Okay. So when we measure the person's height and let's just say for this example the person height in inches, right? So this is supposed to be inches, is 72 inches, right? Okay, so now you actually know what the value of the big X is, and that value of 72 is an observed value of the random variable, right? So it's a standard notation in stats. And the observed value of the random variable big X is denoted as small x over here, right? So you're seeing that the small x is equal to 72, right? Okay, now what you do want to notice is that this small x equal to 72, right, is giving you an idea what the mean is going to be, right? It may not be give you the greatest idea as to what the mean would be, right? So by idea, I mean, well, a more precise term is it's giving you an estimate of what the mean mu is going to be in this expression over here, right? Okay, so this 72 is what's called a point estimate, right, of your parameter, right? That and this is a parameter of your distribution over here, right? Okay, so this is a diagram to give you an idea as to what's going on. X is normally distributed, right? So this is supposed to represent your population over here, right? And your population will have some mean mu over here, right? And if we find one person and we measure that person's height, right? And we put it over here, right? That actually gives us an idea as to what your mean mu is going to be, right? If you think about the values that you're going to get over here, right? So for example, you're not going to get, if you measure, right, you're not going to get, say, like negative values, right? You're not going to get like extremely large values like 1,000 inches or something like that. You will get values that are probably like around 72, right? That are somewhere around, when you translate this into feet and inches, probably somewhere around like 5'8", right? And this is 6 foot, right? 72 inches is 6 foot, right? So probably it's not a good estimate, but it is an estimate of the mu over here, and it is probably better than nothing to start off with, right? Okay, so let's see if we could do a little better, right? In the previous case that we just talked about, what we did is we actually just looked at one person and we used that to estimate the mean mu over here, right? Now, obviously, it would be better if you take a larger sample, right? So a larger sample in stats would probably mean, well, probably more than 30 or 40, right? In the case that population size is so large, right? Say 1.5 million, right? You'd probably be better off taking like several hundred measurements or so, right? Okay, but in this case, for simplicity, we're going to do more than one, but we're just going to do five, so I can write out everything so that you can see, right? Okay, so now what we do is you're going to select five names to the list from the list of Trinidadians, right? Okay, and again, at this point, we don't know the heights as yet, right? Okay, so what we do is we say, well, okay, so big X1, right, is going to represent the unknown height of person 1. Big X2 is going to represent the unknown height of person 2. And so on up to big X5 over here representing the unknown height of person 5, right? Okay, what we do know is, as before, right, each of these over here, right, is it's unknown, right? But this unknown over here is gonna follow a probability distribution, right? And the probability distribution is this exact same probability distribution over here, right? Okay, so each of these is a random variable, right? With a probability distribution that is normal with this mean mu and variance sigma squared, right? Okay. Now, so what this is this is a sequence of random variables, right? The unknowns over here, right? Each with this distribution, right? Any sequence of random variables such as this, right? Where each of the random variables has a certain probability distribution, right? That is based on a certain population, right? Okay, this sequence of random variables, this is a random sample, right? Okay, so that's probably slightly different from what you might expect, right? You might expect, well, when you actually record the values, right? When you go and you measure the person's height and so, right? And say you get values like this over here, right? You'd expect, and these are in inches again, right? You'd expect this to be a random sample, right? But in stats, the correct notation is that just the random variables themselves, the sequence of the random variables is the random sample, right? So it's a notation to start off with, but they actually have good reasons for doing this. Anyway, all right, so this here is a random sample, right? A sequence of random variables. Okay, and what we're going to do is, well, we still want to do the same thing, right? We want to try to estimate what the mean is, what the mean height of the Trinidadians is over here, right? How we're going to do it is, well, if we have these random variables over here, well, eventually what we'd probably want to do is you want to take the average of them, right? And that will, in fact, give us a better estimate of mean mu, right? Okay, the issue is, well, what do I mean by better? And I'll explain that in a second over here, right? Okay, right. So these random variables over here, what you do is you form this expression, right? So these are variables over here, right? And the variables over here, you form this expression where you divide them by 5, right? Okay, now this sort of expression over here is called your sample mean, right, of the random sample, right? And it's a reasonable sort of definition, right? So what you're doing is you're taking the mean or average of these random variables here, right? You have 5 of them, you add them up, and then you divide by 5. Okay, right. Okay, now your big X bar, right, which is expressed in these, you see that it depends on the big X1 to the big X5. So it's in fact a function of the big X1 to the big X5, right? And any function of the random variables from your random sample is called a statistic, right? Okay, so this is the precise meaning. It's sort of interesting that this is the precise meaning of statistic, right? Precise meaning of a statistic is it's a function of the random variables. So a function or expression of the random variables that form a random sample. Okay. Okay. Right. Now, as I mentioned before, each of these follows a certain distribution, right? So it's the same distribution as this over here, right? This was for x, and there's no real difference between big X over here and say x1, right? And likewise for x2. Right? Okay, so each of these xi follows a normal distribution with the same mean, right? Remember, it's a value coming from the same population and the same variance, right? Okay, so that is the distribution of the xi's, right? But if you consider the x bar, right? The x bar doesn't quite have the same distribution, right? What we will eventually show is that the big x bar, right? It's normally distributed with mean mu, right? So like this case over here. But now the variance, in fact, decreases, right? And it decreases by a factor of 5, and this factor of 5 is the length of your random sample, right? You have 5 elements in your random sample, so that's how you divide it minus 5, right? Okay, so, well, as I said, I'll explain where that comes from in our next lecture probably, but how you want to look at this is, well, what you're doing is you're taking values over here. Anytime you take a value, it will have probably some variance, some deviation from the mean, right? And if you take, say, for this one, it'll be probably be on this side. If you take for this one, the variance, the deviation might be on this side over here, right? So by taking a sum of these over here, right, what you're doing is somehow you're letting the deviations cancel out, right? So the positive ones would cancel out with the negative ones, and the end result is what you get when you take the average is that the average would probably be closer to the mean mu over here, right? Okay. All right. Okay, so your variance for the average would in fact be less than the variance for individual observation. Right. Okay. Right. Now let's say we actually so we find 5 people, right? And we measure the heights, right? Okay. And we measure the heights like this over here, right? I wrote it like this in sequential order for simplicity, but it isn't necessarily going to be like this for this case, right? It is possible that, say, the first one could have been 71 and so on, right? Anyway, so each of these, right, notice I use small x over here. So, for example, small x1, which is 65, is an observed value of a random variable big X1, right? So I'm using the same sort of setup and ideas as in the first case, right? All right, so your small x1 is 65, small x2 is 66, and so on, right? So these are observed values of your random variable over here, right? Right. Okay. And once you have these observed values, right, what you could do is you look at this expression, and what I'm looking for is an observed value of the big X bar, right? So essentially, what that means, well, this equation over here is really just the same as this equation over here, right? Except now what I'm looking at is observed values, and if it's observed values, I use the lowercase letters instead of the uppercase letters over here. Right? So the uppercase letters are for the random variables, and the lowercase letters are for the observed values. Right. Okay. So what I want is the observed value of this big X bar, right? And how I get it is, well, I use the lowercase version, if you want, of this equation, right? And you feed in your observed values, and when you feed it in over here, what you're doing is you're just taking the average of these observed values. You have 5 of them, right? And you get 68, right? Right. Okay, so your small x bar over here equal to 68, right? Is an observed value of the big X bar, right? Okay, so let's recall that the big X bar is the big X bar over here is normally distributed with mean mu, but with a different variance over here, right? But the key thing for us for the time being is that it has the same mean mu, right? Now this over here is a graph indicating the PDF probability density function of the big X bar here, right? Right, so this is the PDF of just the X, and this is the PDF of X bar, right? Okay, and notice that this one, both of these are centered about the same mean mu, right? But this one over here has less dispersion about the mean mu, right? And that's corresponding to the fact that the variance over here is sigma squared on 5 is less than sigma squared, right? But as I said, the key thing over here is that the mean mu is the same, right? So when we get this observed value over here of 68, right? What we're actually getting is we again getting an estimate of the mean mu, right? And this estimate over here is in fact going to be a better estimate. Most of the times it is going to be a better estimate, right? Okay, so why is it going to be a better estimate, right? So suppose you repeat this experiment again, right? So you know, again, you select next day, you randomly select 5 people from the list. It may not be the 5 people, same 5 people, right? And you record the heights and so on, right? So you may not get these values again. You again work out the observed sample mean, which is a small x bar, right? And you get an x value, right? May not be on this side, may be on this side, and so on, maybe over here, right? But you see the fact that the variance of this is smaller, right, means you're less likely to deviate from this sample mean mu over here, right? In this case, because the variance is larger, right, you would be, if you're just using, say, a single one to estimate, right, you'd be more likely to deviate from the mean mu, right? So the fact here that the variance is smaller, right, means that when you work out this value, your chances are you're closer to the mean mu, which means that your estimate over here is going to be better, right? Okay, so that's what this is saying over here in this paragraph, that uh, big X bar is a better estimator, right, of mu than just using a single observation, right? Because your variance of the big X bar is smaller than the variance of X, right? Right, so what we did here is we estimated this small X bar was estimating this mean mu of your population, right? Right. Now, if you notice, uh, so really what we want to do is we want to estimate that mu over there, and we want to estimate the we want to estimate the mu start off with, right? But also we would eventually want to estimate this variance over here, right? Okay, so how do we estimate that variance? Well, use a similar idea, right? What we do to estimate the mean mu, right? We use this expression, right, or this statistic over here, and it turns out this is a good estimator of the mean mu, right? Taking the average value of your random variables. If you want to estimate the sigma squared, if you want to estimate the variance, right, then you'd need to use a different expression, right? This one isn't going to work, right? And the expression that you're going to use is you're going to use this over here, right? Okay, so and it makes sense, right? What you're going to do is, well, when you estimating, right, if you actually get your values, right, what you would say you calculate your sample mean first, right? And then what you're doing is you're measuring the difference of your values from the sample mean, right? And then you're squaring that. Okay, so this is the deviation from sample mean, not actual population mean, right? Okay, and you're squaring that, and then you're adding up all of those, and that's actually measuring squares of deviation, right? So this over here is giving you an idea of the overall sort of variance from the mean, right? Okay, so anyway, but you could take this. This is your definition of how you would estimate this sigma squared over here, right? Okay, so this sort of expression over here, right, which can also be expressed as this, right, using a certain amount of manipulation. This is done in the course notes. Okay, so going from here to here is done in your course notes over here, right, by expanding out the squared and so, right. What you're doing is you're using properties of x bar and so on, right? So you could take a look at this if you're interested in being able to go from here to here, right? Why you'd want to use this instead of this, right, is, well, you see over here you need to calculate the x bar first of all, right? And once you observe your values and so on, right? But over here you don't actually need to calculate the x bar first of all, right? What you need is to sum the xi's first, and then you sum the xi squareds, right? Okay, so in a way you're avoiding the calculation of the x bar first of all, right? And sometimes these expressions over here are more easy to compute or could be given to you, right? Rather than this big X bar. But anyway, either one would work, right? And this is the one we'll use in this example, right? Okay, so this is, so far, each of these are big X's, right? So it's a big X bar over here and big Xi over here, right? These are actually coming from your, these big X's are coming from your random sample. This is an expression over here, and this is an expression over here. So this is a function of these variables over here. So this is any function of the random variables from your random sample is called a statistic, right? So this s squared over here is a statistic, Okay, and this particular statistics is called sample variance, right? Okay, right. So far it's a statistic, right? And then what you could do is you could use your observed values of this to calculate the observed value of the S squared, right? Okay, so again, this equation over here, basically you're just going to convert it to lower caps, right? And you put in your observed values, right, into this expression. As I said, with this expression here, you'd need to know what the mean is before, but we did actually work it out here, 68, right? And you say, so you start off with the 65 minus 68 squared, right? And then the 66 minus 68 squared, and so on, right? You add up all of these squared terms, and then you divide by, you have to be a little careful here, right? So you're not dividing by 1 on n over here, and n is your sample size, right? So sample size is 5, right? Okay, you divide it on 1 on n minus 1, right? So this is 1 on 4 here, right? When you divide this expression over here by 4, you get 6.5, right? And this 6.5 is now an estimate for your sigma squared, right? And if you wanted to get the sigma, well, then you take the square root of the 6.5, right? Okay, so this s squared, this over here is an estimator for your variance sigma squared. And the big X bar over here is an estimator for the mu, right? So you have two different estimators or statistics, right, for your different parameters of your distribution. Okay. Right, okay, so what we did so far is we were estimating this mu and sigma squared, right? So let's just recap and introduce some more notation here, right? Okay, so your unknown, if you find the name of a person, right, and you don't know the height of the person as yet, right? Then that height is an unknown, right? So we give it a name which is the big X, and part of a statistics over here is you assuming that that big X has a certain type of probability distribution, right? If you think it's a big assumption, yeah, it is an assumption, but that's just what we work with, right? Okay, so your big X over here has this normal distribution here, right? Okay, and we mentioned that when we now form big X bar by taking this sort of this sample mean here, taking your average over here, what happens is that the variance changes, right? Okay, so your big X bar has a smaller variance. Again, it's normally distributed, right? Now going from here to here takes a certain amount of justification, right? And we'll explain this in our next lecture, right? But for the time being, you want to realize that your big X bar is again normally distributed. Same mean mu, but the variance is different, right? Okay, so this is a distribution, right? Associated to a statistic that is based on your random sample, right? So this distribution over here, because it's based out of something that's coming from your random sample, right? So your big X bar is coming from the random sample here, right? This type of distribution is called a sampling distribution. Okay, right. Okay, now similarly, so your big X bar was an estimator for mu, right? And we saw that your sample variance over here, which again is formed by using random variables from your random sample, right? This big S squared over here is an estimator for sigma squared, right? Okay, so this big S squared, right? Seeing that is it's a function of random variables, it is itself a random variable, right? A function of random variables is again going to be a random variable, right? But the question now is, well, what's the distribution of the big S squared, right? So To recap very quickly, the big X bar, right, which is a function of the random variable, had a certain distribution, right, that was similar to this one. So similarly, the big S squared is going to have a certain type of distribution, but it's no longer going to be normally distributed, right? The, why it's not going to be normally distributed is because you see you're taking squares over here, right? And once you start taking squares over here, things get more complicated, basically, right? Okay, so your big S squared over here is essentially it's going to have a certain type of distribution once you scale it properly. So you need to multiply by 4 and you need to divide by the known standard deviation, right? Okay, so your big S squared over here, once it's scaled appropriately, will have something called a chi-square distribution, right? So how you denote your chi-square distribution is this is Greek letter chi, right? Uh, Chi, and it's a square over here, and then you have this index here, and that index is telling you what the degrees of freedom are, right? Degrees of freedom you could understand in terms of vector spaces, and that's actually I wrote that up in your notes. If you're interested in knowing what precisely degrees of freedom are, right, it's here in your notes, right? This gives an interpretation of what it means. You need to use a certain amount of idea of like vector spaces and subspaces, right? Right. But the main thing that you want to know, it has a certain amount of degrees of freedom, right? Okay, so S squared over here, once it's scaled appropriately by these scalars, is going to have a chi-square distribution, right? Now the chi-square distribution we're not going to use too much in this class, right? The main place that we're going to use this chi-square distribution is usually, well, basically you use your chi-squared when you derive an t distribution, right? So your t distribution, well, this guy over here is the one that we would really focus on, right? Anyway, so the main thing over here is that the S squared essentially has a chi-square distribution, right? Provided the S squared is scaled, right? Okay, so this statistic over here, which is used to estimate variance, has essentially a chi-square distribution. Now, there are other statistics that could be constructed from your random sample, right? And one of them is you take your X bar over here, right? Right, and remember the big X bar is formed from your random variables like this, and what you could do is you could subtract the mean mu, right, provided that you know it, and divide by a standard deviation, known standard deviation, if you do know it, right? And you also divide, well, over here when you divide in by standard deviation divided by square root of n, where n is your sample size and the sample size is 5 over here, right? Okay, so what you're doing over here is you have basically what you're doing is you have big X bar over here with mean mu, and what you're doing is you're subtracting mean mu, big X bar, you subtract the mean mu and dividing by the standard deviation of this, which is sigma and root 5 in this case. And you should remember from a previous lecture, what that is doing is that's going to standardize the big X bar and convert the big X bar into a standard normal and a standard normal. So in other words, it's converting this into a Z over here, which is standard normal. And the standard normal, remember, has mean 0 and standard deviation 1, right? Okay, so why we would want to do this is, well, this sort of expression over here, right, is used extensively in the rest of this course, right? So you use this when you form in confidence intervals and when you're doing your hypothesis testing, right? We're not really going to use chi-squared over here, right? You use that in other situations, not in situations that we consider in this class. Okay, so the last one that I want to look at in this sort of introductory lecture is So with this over here, right, if you form in this expression, you assuming that you know what your standard deviation is over here, right? So your standard deviation is for your original population, right? So this is the probability distribution for your original population. But sometimes you just don't know it, right? So what you'd need to do is you'd need to estimate it, right? But you see, it's not too bad, right? Because the big S squared actually is, we talked about this, was an estimator for the sigma squared, right? So just the big S by itself is an estimator for sigma, right? Okay, so if I don't know what the sigma is, I can use big S instead over here, right? So I get this expression, right? Now this over here is a function of random variables like this, and the big S over here, right? If you take square roots here, is also going to be a function of random variables, right? So if you consider you take a square root over here, and the S is going to be the square root of this, so the S is a function of random variables over here, right? So this entire thing is a function of random variables, which isn't particularly simple, right? But this over here and this over here have the same sort of basic form, right? The only problem is this is unknown and needs to be estimated, right? Okay, so the big X bar had a, if the X has a certain type of probability distribution, the big X bar has a probability distribution that's related to the big X, right? Similarly, the S squared has a probability distribution which is related to this. It isn't straightforward to see, but it does have probability distribution related to this, right? And likewise, this one over here is going to have a certain type of probability distribution, right? And the probability distribution, it is something close to a normal distribution, right? And it's somewhat close to a standard normal, right? But it isn't quite a standard normal, and the probability distribution over here depends on the size, your sample size over here, right? Remember, our sample size that we're talking about in this example is 5, right? Okay, so this over here has a t distribution, right? Which looks something like a normal distribution, and it has a index over here, right? And this index you'd need when you're using the tables for t distribution. It has an index based on the sample size, right? And the index is n minus 1, right? So yeah, this over here is a t distribution with n minus 1 degrees of freedom, right? So it's the same idea over here with n minus 1 degrees of freedom, right? Okay, so both of these, so okay, so this over here has a certain distribution, and this is a sampling distribution for this statistic, right? And this one over here, we're using the big S instead of the sigma, right? This has a certain distribution over here, which is a t distribution. And this distribution is again a sampling distribution associated to the statistic, right? So if you want to be seeing examples of four sampling distributions, right? We have four different, for your population over here, when the big X has this normal distribution, we have four different statistics, right? We have this one over here, which is a sample mean, and it has this sampling distribution, right? This normal sampling distribution. You have this statistic over here, S squared, right? Which has a chi-squared sampling distribution. You have this one over here, which is standardized sample mean, right? So you're standardizing to standard normal, right? And this is your sampling distribution for this statistic. And then finally, you have this one over here, which is similar to this one, right? This is a statistic with this sampling distribution, right? And the last two we're going to use uh, extensively for the rest of the course. Right. Okay, so let's use the examples that we just did, right? Put some context to these definitions that we need to go through, right? All right. Okay, so this is from your notes, section 9.3, right? Okay, so a population is a set of observations with which we are concerned, right? So in this example that we just did, right, the population that we were interested in was in fact the heights of all Trinidadians. Okay, right. The parameter is a quantity, right? That is a property. So the term parameter is used to denote a quantity, and theta, right? So theta is just a name, right? That is a property of your unknown population probability distribution, right? Okay, so this is your probability distribution, right, for your population, right? We said that the height of each person, if you didn't know it as yet, then that's going to be a variable, and it's going to be a random variable, right? So you didn't measure as yet. So you expect that when you measure, you have a probability of values that x can take, right? And that probability of values that x can take is given by some probability distribution, right? So this is the unknown population probability distribution, right? Over here. And why it's unknown? Well, for us, it's unknown because we don't know the parameters here as yet, right? And the goal of stats is you're trying to estimate these parameters here, right? Or the goal of the stats that we do in this course is we want to estimate your parameters here, right? Okay, so examples of parameters for a population probability distribution is, for example, the mu over here and the variance sigma squared, as discussed here, right? Right. A statistic, right, is a function of the random variables in a random sample, right? Okay, so that's what we talked about here, right? This is your random sample. Remember, we say we had a list of all the Trinidadians. We selected 5 names from the list, and we didn't know what the heights were of each of these as yet, right? So we gave it variable names, and that was x1, big X1 to big X5, and this is your random sample, right? Each of these are random variables, so a random sample is just a sequence of random variables. Okay. Now, once you have your random variables over here, what you could do is, well, you're using these to estimate your parameters, right? So we talked about using this big X bar, right, which is formed from these random variables to estimate mu, right? So the big X bar, which is a function of these random variables, that is a statistic, right? Right, and an estimator is just a certain type of statistic that is targeted towards finding a population parameter, a certain population parameter, right? So this big X bar, it's a statistic, right? But it is targeted. Why we created something like this is we're going to use it to estimate what this mean mu is over here, right? So when we do our measurements and so on, right? What we do is when we do our measurements and we get values for these big x's over here, we use it to calculate and your big those values over here, use it to calculate an observed value for your big X bar, right? What you're doing is you're getting an estimate over here for your big X bar, and this estimate over here is meant to be an estimate for the mean mu, right? Okay, so the big X bar over here is an estimator, right, for a population parameter mean mu, right? And this is sort of notation. The population parameter is just theta, right? So this is meant to be some value, and once you have theta hat, right, the estimator is as a statistic, right? So this over here is a random variable. So the key thing that you want to realize over here is that this is what you're trying to estimate, right, the theta, and this is your method of getting the estimate, right? And this here is a random variable, right? So this is a value over here, and once you have the hat over there, theta hat, right, this is supposed to indicate that it's a random variable. A point estimate of your parameter, right? So this over here, when you obtain this value 68, right? This over here is meant to estimate this mean mu, right? So this is a point estimate, right? And we said that we actually talked about that already, right? So this is a point estimate of the mean mu, right? Eventually, what we will get to is we will get to say interval estimates. In other words, confidence intervals, right? But for the time being, this is a point estimate, right? Right. Okay, and examples of estimators are the big X bar, right, which we saw already, right? And you can also, the big S squared is an estimator for variance, right? Okay, so for this variance over here, we can use S squared to estimate it, right? Okay, so examples of estimators are your sample mean, which is the big X bar, and the sample variance, right, which we talked about over here, right? So the big S squared is an estimator for population variance, right? Okay, so one thing that we need to look at is this idea of an estimator being unbiased, right? Okay, and in order to do that, what we'll do is we'll consider this example here. All right, okay, so what we want to do is we want to understand this notion of an estimator being unbiased, right? Okay, so your estimator theta hat, right? What it's trying to do is it's trying to estimate a certain parameter theta, right? So for example, big X bar is an estimator for a parameter which is the population mean mu, right? Right. Okay. Now your estimator is good in a sense, right? If it is unbiased, right? So this theta over here said that theta hat, right, is a random variable, right? And if it's a random variable, you can take expected value of it, right? So your normal definition of expected value, right? Uh, uh, if the expected value of the theta hat is equal to the parameter of your population, right, then the estimator is said to be unbiased. Okay, so let's look at this example here, right? All right, so I have x1 and x2, right? This is a random sample, so each one of these are random variables, right? And it's going to have some probability distribution. It's going to have a probability distribution, say like this big X over here, it's going to have some probability distribution. They're not saying that the probability distribution needs to be normal over here, right? And you need to be aware when you're doing some of these problems is sometimes. Okay, so the big X1 and the big X2, right, are random sample. Each one of these are random variables with some population probability distribution. Right? Okay, so that's similar to this over here, this big X, which is the unknown height as yet of a Trinidadian, is has this population probability distribution here, right? Okay, right, and this population, this big X over here has the expected value of X over here, right, is the mean of X, and the mean of X is going to be mu over here. However, over here, right, It's not specified. You are given that that the population is going to have some mean mu, right? And that's pretty standard, right? You're not given that the big X and the big X1 and the big X2 are normally distributed, right? And you don't actually need that in this case, right? And when you're doing questions in statistics, sometimes you will need to distinguish between cases where something where you know that the population is normally distributed and when it may not be normally distributed, right? And over here, nobody is saying that it is normally distributed, but you don't actually need it, right? Okay, so all three of these are supposed to be estimators of the mean mu, right? Okay, so all of these over here, right, are estimators like this of your parameter, which is mu, right? And what you want to do is you want to check to see if the expected value of these is equal to mu, right? Right. Okay, so this first one here, you want to notice that this estimator is formed, your random sample is of size 2, right? And all you're really doing over here is you just take an x1 plus x2 and you divide it by 2, right? So it's a pretty small random sample, right? Probably not practical, but it's still a random sample here. And what you're doing over here is you just take an sample mean, right? Similar to this over here. What you in this case you had a sample size of 5, here you have a sample size of 2, right? Okay, so this one is standard. This is actually the same as x bar, right? This one over here, right? Okay, so the weighting in this case was you had half half, right? And in this case over here, for some reason, they decided to have weighting of a quarter over here and a weighting of 3/4 over here, right? So, and in the end, the weighting still add up to 1 as over here. Half plus a half is 1 and a quarter plus 3/4 is 1, right? So this one doesn't seem unreasonable idea also as an estimator of mu, right? However, this scaling factor of 3/4 is a little strange, right? And it turns out this one, well, both of these are going to be unbiased. We'll show that in a second, right? But the problem with this guy is that the variance in this case would be larger than the variance in this case. We're not really going to get into that. So this one over here would in fact be a better estimator, right, than this one here, right? Anyway, this one, however, this is a little strange because I mean, what you're doing is you're using the big X1 and the big X2 like this over here to try to estimate the mean mu, right? But well, where's this 9 coming from, right? Right. Okay. So anyway, so if we want to check to see if something is unbiased, this is what we use over here, right? So you'd need to take expected value of the estimator, right? So in the first case, right, and okay, so before we get to it, right, you want to remember that each xi, right, has some probability distribution, right? I'm not saying it's normal, but just some probability distribution, and the mean it has a probability distribution is going to have a mean mu, right? And so expected value of the big x1, right? X1 is a random variable with a certain probability distribution. And by definition, the expected value of x1 is mu, right? And likewise, x2 has exactly the same probability distribution as x1, right? So the expected value of x2, when you work it out, is also going to be mu, right? All right, so we're going to use this fact over here, right? Anyway, so we check in to see if the estimator is now unbiased, right? So this is your first estimator over here, right? So what you do is you take expected value of this, right? So take expected value of your estimator. Your estimator is x1 on 2 plus x2 on 2. So you take expected value of this. You want to work out expected values, right? Of this over here, right? We know, okay, so this is your definition of expected value. Say in the continuous case, it's this integral over here. But this here is not what we want to use in this case, right? What we want to use is this sort of expression over here. So we want to use properties of expected value, right? So properties of expected value is if you have a sum of random variables would possibly have coefficients in it, right? And you have a constant over here, then the sum will break up like this over here, right? So we can use that over here, right? In this case, this has no constant, so the c is equal to 0. Okay, so all you're doing is it'll break up using the plus here, right? And then the constants, a half and a half, right? Okay, so you split this up using this property over here. And then once you split up like this, the expected value of the big X1 and is mu. Similarly, expected value of the big X2 is mu, right? And you get a half mu plus a half mu, which is mu, right? So you get the expected value of your estimator is the parameter that you want, right? So this estimator is unbiased, right? Okay, so let's take a look at this second case over here, this second estimator, right? So this second estimator, again, what we want to do is we want to check to see if your expected value of your estimator is equal to the parameter that you're interested in, right? All right. Okay, so expected value of your estimator, you work it out as before. So you take an expected value of your expression for the estimator, right? Again, you use your linearity over here to split this up, right? And when you split it up, the quarter comes out over here, the three quarter comes out over here. The expected value of each of these is still mu, and you get a quarter mu plus three quarter mu, which is again mu, right? So this estimator over here is again unbiased, right? So you want to notice that this one is different from this one. Both of them are unbiased estimators. So both of them work uh, in some sense to give you the same estimate mu, right? But it turns out that this one over here is actually better than, say, using this one here. Right. Okay. And finally, what we want to do is we want to look at this estimator over here. Right. So you use the same idea. You take expected values. You use your linearity to break this up. Here you have this constant now, right? But this formula here allows you to deal with the constant. So the constant is just going to come out like this. And now once it splits up like this, you just put in your mu here. You put in your mu here, right? This 1 6 plus it's 1 6 mu plus 1/3 of mu, which would give me mu on 2, right? And then plus 9. So I get this expression over here, and this one is not equal to what I'm interested in, which is mu, right? So expected, if this is going to be an estimator for mu, right, it is not unbiased, right? Because your expected value of this is not mu, right? So this one is not an unbiased estimator of mu, right? So it's a biased estimator. Okay. Right. Okay. So last thing we want to do in this section here is we want to show that this general expression for sample mean, right? So by general, I mean this is sample mean where your random sample over here could be any size small n here, that this over here is an unbiased sample mean, is an unbiased estimator of mu. Okay. All right. Okay, so you want to notice that we did that already in the case when n is equal to 2, right? Here, if you look at this expression and you look at this expression here, right, and you put small n is equal to 2 into this, you'll actually get exactly this. And we showed that when you take expected value of this estimator here, we end up with a mu, right? So something similar will happen in this case here, right? So let's see what it is. Okay, so my big X bar is the big X1 added up to the big Xn divided by the small n, right? Okay, so it's a sum of all the big Xi's divided by n, and that is what I have inside here, and I'm taking expected value of it, right? Okay, now when I'm taking expected value of a sum, right, I can use this linearity property to break it up. So expected value of a sum is sum of expected values. So that's how this summation sign will come out over here, right? The one on n, the scalar can come out like how the scalar comes out over here. Now what I have is 1 on n, and I have a summation of expected values here, right? But each of these xi's has the same probability distribution, which means that they have the same expected values, and each of those mu, right? So what you're doing here is you're adding mu to itself n times, right? And that just is just going to work out to be n times mu, right? And now here you have 1 on n times n mu. So the n's are going to cancel and you end up with mu, right? So expected value of the big X bar over here is equal to mu, which shows that the big X bar is an unbiased estimator of mu.